Okay, for the last talk of the day, we have Soheil, who will be telling us about algorithm solved clustering lesson from Behnezhad.
Thank you. I wanted to start by thanking the organizers for putting together this amazing workshop. And thanks for inviting me. Today, what I'm going to talk about is some lessons that I've learned working on sublinear graph algorithms that have been applicable to clustering algorithms. And what I talk about is based mainly on a joint work with Moses, Anna, and Weiyun. Although I mentioned some other works that I feel the appropriate reference for. Okay, so the talk has two main parts. The first part is about sublinear graph algorithms. It has nothing to do with clustering. But as we'll see, the machinery developed for these sublinear graph algorithms is super useful for clustering algorithms. I believe there's a lot of potential for much more to explore here, so I'm hoping that maybe we can find some application in this workshop. And the second part of the talk, I talk about the applications, in particular one application in correlation clustering. Okay, so let's get into sublinear graph algorithms. So what do I mean by a sublinear graph algorithm? These are algorithms that have query access to the graph. And the goal is to solve a graph problem, for example, a maximum matching, spanning tree, pick your favorite graph problem. We want to solve this graph problem without querying all of the graph. So we do not want to see the whole graph, yet we want to solve a problem at hand. Okay, and there are often two types of query models that people study for graphs. There are other models as well, but these are the most common ones. The adjacency list model or the adjacency matrix model. I'm sure everybody knows what these are. So for example, in the adjacency matrix model, we can query if a pair of vertices are adjacent or not. We can query adaptively. The only goal, is to query a small number of entries. Do not query everything, basically. We want sublinear in the size of the graph, maybe sub-quadratic in the number of vertices. Okay. So I'll particularly start talking about the matching problem. This is a very well-studied problem for in the sublinear time model, for which a heavy machinery has been developed that's been useful also for clusterings. So what is a matching problem? Just a quick reminder, a matching in a graph is a collection of vertices from edges. The red edges here form a matching, and we're interested in a matching of largest possible size. That would be the maximum matching of the graph. Immediately there is a barrier or bad news that n-squared queries are needed for finding not just a maximum matching, but any constant approximate matching. So in other words, it's not possible to obtain a sublinear algorithm for finding matchings. But the key word here is finding. The lower one only holds if you want to find the edges of the matching. You report all the edges of the matching. In other words, there's a good news that if we only want to estimate the size of the matching, then we can now do non-trivial things. And this is an extremely active area of work that if you want to estimate the size, you can actually achieve sub-quadratic time algorithms. So let me start by giving you a sample of results that can be achieved. So in 2001, I showed that a half approximation of the size of maximum matching can be obtained in order n time, n times some polylog. So n is the number of vertices, much smaller than the number of edges, which could be as large as n squared. And this matches the lower bound from 2007 by Parnas and Ron, which shows omega n time is needed for any constant approximation. And if you're looking for open problems here, there's an immediate open problem that I think is a very nice one. Can we obtain better than half approximation in order n time and polylog n time? This is open. We could also ask, what about just sub-quadratic algorithms? What's the best approximation that can be achieved? There's been a sequence of works. There was a really nice Fox 23 paper by Bhattacharya, Kish, and Saranurek. They showed indeed you can get a Von Mises approximation with sub-quadratic time, n to the 2 minus some f of epsilon. And in an upcoming joint work with Mohammed Rovani and Aviad Rubinstein, we show that the algorithm of BKS is actually optimal. That if you want a really good approximation, approximation, then barely subquadratic is the only thing.
The F
Remains the same. It is not the same F, but as you make epsilon close to 0, they both go to 0. So qualitatively it says if you want very close to optimal solution, then near quadratic is optimal. Yeah, but there are a lot of there's a huge gap between the two F's. Okay. Right, so let's see how we can estimate the size of the solution without actually constructing it. So here's the whole framework. Suppose that we fix some matching of the graph. Could be different matchings. We have a choice of an algorithm to fix this matching. We do not know what this matching is, but what we want to do is we want to define an oracle such that given a vertex P, it can tell us if that vertex is matched in M or not. Okay. So if we have such an oracle that ideally does this without constructing the whole matching, the way we can use it is we can run this oracle on some random constant number of vertices, look at what fraction of them get matched, use that as a proxy for the fraction of vertices in the whole graph that are matched. Okay, so the question is, what's the query complexity of the oracle and for a given random vertex? So we pick a random vertex, how much time does it take to verify if it is matched or not by this matching M? And this also depends on the choice of the matching M, which matching we fix, how does the oracle work? So these are the things we have to fix to answer this question. So
what kind of variance this could have?
So that's a good question. So the result I mentioned last slide, they work both in the adjacency list model and the adjacency matrix model. So in the adjacency matrix model, you also have to give up an additive epsilon and error. You do not have to give the adjacency list model.
So maybe I could say, if I have a single edge incident to a vortex, then I'm trying to find it.
Yeah, in the adjacency matrix model, you cannot do that. That's why you have to give up an additive epsilon and error. But in the adjacency list model, you can do that.
Yeah, I just get the first.
Yeah, great. Yeah. So if you assume that the matching is large, you can do trivial things in the adjacency matrix model as well. All right, great question. Any other questions? Okay.
Did you assume that these units are sorted from that?
No, it could be arbitrary.
It doesn't matter at all?
The lower rounds hold even if the adjacency lists are randomly sorted, so I don't think it matters much. Right, so let's see one choice of this matching M and then the oracle. So the greedy algorithm for matching basically processes the edges in some order. Here's an ordering over the edges, and then what we do is we go over the edges in this order. Whenever we visit an edge, if we can, we put it in a matching. So the first edge is always going to be added to the matching. The second edge we cannot add it because it's incident to a matching edge. We continue so on and so forth until we find what we call a maximal matching, not necessarily a maximum matching. Nonetheless, a maximal matching is at least half the size of a maximum matching. It provides a half approximation. So to provide this half approximation, now it suffices to specify how the oracle works and what the complexity of verifying whether a vertex is part of the matching model is. And the insight, the key observation is that an edge E is part of this matching M if and only if there's no other incident edge with a lower rank that's part of the matching. That's what the greedy algorithm guarantees. So for example, this edge 6 is not part of the matching because there's a lower rank edge 5 incident that's part of the matching. So this naturally defines a recursive query process to determine if an edge is part of the matching or not. And this was first considered by Onat and Nguyen in a Fox 2008 paper. So for example, if we want to tell if edge 11 is part of the matching, we recursively query one of its edges, one of its incident edges. And between them, naturally, we want to find the incident edge that's part of the matching as fast as possible. So we'd like to query the ones with a smaller rank first. So we first query edge 6. 6 recursively queries 5, then 4, then 3, 2, 1. But the moment we reach 1, we know that it must be part of the matching because it doesn't have any lower rank neighbor. And 1 being part of the matching tells us 2 is not, 2 not being in the matching tells us 3 is, and so on and so forth. So we backtrack all the way back to 11. But 11, okay, sees that 6 is not part of the matching, but is not still sure if it's part of the match. So it also queries 10. And it turns out that for edge 11, this is actually not really better than just running the whole matching because we recursively will explore the whole thing. But if instead I started from, suppose that I queried instead edge, instead of that, suppose that I queried edge 12. So now, yeah, so now if I query edge 12, the moment that it queries 9, it sees that as part of the matching. So we won't actually query 11 or 10. So the size of this subgraph that we explore is going to be much, much smaller for 12. So now the question is, what's really the typical size of this? Maybe like if we randomize this permutation over the edges and pick the starting vertex at random. Okay, so let's talk about this now. So let's use Q, V, and pi to denote the number of the size of the subgraph explored for vertex V according to permutation type. And let's use delta to denote the maximum degree of the graph. So already in the paper Onat and Nuran, who introduced this recursive query process, showed that Q, the expected value of Q is upper bounded by e to the delta. So it's not impressive if delta is large, but if delta is constant, you explore only a constant size subgraph and tell if the vertex is part of the matching graph. And a year later, Yoshida, Yamamoto, and Ito in Stock 2009, with an ingenious analysis, significantly improved this to polynomial, like delta squared, for a with the extra assumption. So they use the fact that the starting vertex is random. So if you use the fact that the starting vertex is random, they were able to prove an upper bound of delta squared. In our application, the starting vertex is going to be random, so it's as good for our application. And this is nice because now we don't want delta to be necessarily constant, even if delta is super constant, but just smaller than n, we'd get a subquadratic algorithm. And the result I mentioned earlier, the 2001 result that I had, I basically tied in this up to a log n factor, so that it's upper bounded by delta log n and also lower bounded by delta. So for a random vertex, it just takes delta time almost to tell if it's matched or not. And you can run this on a constant number of vertices to estimate the size of the match. Okay. So the key takeaway out of this is that randomized greedy algorithms are extremely helpful for designing sublinear time algorithms, and they have a strong locality guarantee that to determine if a vertex is matched or not, it suffices to look at a small local neighborhood of that vertex. Okay, so this was the first part of the talk, and I want to say that this machinery of bounding these local neighborhoods that are relevant to tell if the output of a vertex, what the output of a vertex is, can be super helpful for a lot of applications. And today I'll talk about such applications in classroom.
Yeah, so there is a question from chat. The question is, are those the same randomized greedy algorithm only with analysis, or are they different algorithms?
So the algorithms are exactly the same. It's just the analysis of the algorithm. The oracles are slightly different, but the oracles both are trying to answer the same question of whether a vertex is part of the output of the randomized greedy maximum matching algorithm. Yeah, great question. So it's just an analysis, almost. Yeah.
You mentioned that the Onat and Weiyun thing was for any vertex.
It's for any vertex. The two follow-up crucially use the fact that the starting vertex.
And do we have a better sense of want the correct answer for any vertex?
That's a very good question. I've thought about it a lot. I do not know what the answer is. I know it's at least delta squared. So there is a gap. Yeah. So there's an example, it's at least delta squared.
There's a question in the chat, are those the same randomized region?
Yeah, I answered.
Oh, you did answer.
Yeah, proving any poly delta bound for a given vertex would be extremely interesting. So you do not even know poly deltas. Yeah.
Even though you take a random vertex, you still depend on the maximum figure in the graph. So like you have any
That's a good question.
like the fraction of vertices with high degree, like so it's more.
Yeah, it's not really max degree, it's average degree.
Oh really?
Yeah. So the upper bound is average degree. The lower bound is also, although the lower bound could also be average.
Actually, looks we are asking, but so is the Yoshida also added in these?
If average degree comes max degree.
Nice try.
Yeah. Yeah. All right, so now let's get to part 2, which is the applications for clustering. So I started talking about correlation clustering, parallel algorithm for correlation clustering, where this machinery you use it to analyze the approximation ratio of an algorithm. And how much time do I have? 15 minutes, okay, good. So this is the first talk on correlation clustering, so let me define the problem. And let me right away say that this is not the most general version of correlation, because this is the complete variant where all pairs are labeled. The complete variant of correlation clustering, we can model it as a graph problem. You're given a graph G. Basically, edges in the graph represent similarities, and non-edges represent dissimilarity. So if a pair of vertices are adjacent, we want to cluster them together intuitively, and if they're not adjacent, we want to separate them as much as we can. Okay, so formally, what's the goal? The goal is to cluster the vertices into arbitrarily many number of clusters. So there's no like k means or k median. So the only input is these labels on the pairs, and now we want to put them in arbitrary many clusters such that the number of mistakes is minimized. And what is a mistake? A mistake is either an adjacent pair that's separated or a non-adjacent pair that's inside the cluster. So let's see examples. So here on the left, the graph is just a collection of disjoint peaks. These inputs are great because we can just put each of these peaks in a different cluster, and the cost is 0. It turns out the cost is only 0 on collections of disjoint peaks. The graph on the right, this I think is the optimal solution. It has cost 5 because there are 2 edges crossing and 3 non-edges inside. Okay, so this is the correlation clustering problem. I won't talk about the history of the problem. I don't have time to talk about that. But there is a famous pivot algorithm that obtains a 3 approximation. And it's also super useful in rounding LPs for the problem. So even better approximation can be achieved using this as a rounding algorithm. So what is the pivot algorithm? It was introduced by Weiyun, Charikar, and Newman in stock 2005. So the algorithm starts by picking a random vertex V, say the red vertex on the bottom right corner. What we do is then we put it in a same cluster with its neighbors and remove them and recurse. So we remove them and then we pick another remaining vertex, cluster with its remaining neighbors, and so on and so forth. And this is a 3 approximate algorithm. So they prove, Weiyun, Charikar, and Newman prove that this is an expectation, a 3 approximation. And the one problem with this algorithm is that it's too sequential. Every time you're picking one pivot for one cluster, and we could be in a scenario where we actually have to add the n clusters. So in those instances, the algorithm would take n rounds. So the question is, can we obtain a good approximation if you preferably maybe constant number of rounds or not? So that's the question I talked about today. We could also talk about better approximations. This is a problem that Alma will talk about tomorrow. So today I only talk about round complexity of pivot, and can we improve it any further? Okay, so this is the result that I talked about today with Moses, Anna, and Weiyun. We showed that for any epsilon, for any positive epsilon, there is indeed a constant round, 1 over epsilon round implementation of a variant of the pivot algorithm that obtains a 3 plus epsilon approximation. And the analysis of the approximation ratio crucially relies on locality of randomized screening and the upper bound of Vichy et al. Okay, yeah, so there was a long line of work on obtaining faster running times. There's been also some follow-up work that I forgot to add to this table. But basically, there were 2 lines of work before. There were algorithms obtaining 3 approximation or almost 3 approximation, and polylog or log rounds, depending on the setting. And there were large approximation in constant round. So this is a constant approximation. This is a constant round algorithm. It's almost 3, so achieves the best. So
Basically, doing this in top, or is there, you mean both like in MPC and in semi-streaming, like passes in streaming?
So yeah, so when we talk about rounds, we have to be specific about the model. So these results are for different models. So these columns show if these algorithms work in that model.
Yeah,
So for example,
at the top, like the last row. Okay. I mean,
this one,
the very top is like the box, right?
yeah, this one. Oh, yeah. So this works in
Both
all
models.
3. Yeah. In the local model, semi-streaming and stuff. Yeah, for semi-streaming, there was a follow-up 1 pass algorithm of 3.
Or 3.
Yeah. So 2 follow-ups. Yeah.
And the spaces and polylog for the semi-streaming or
Settings over.
It is N.
Usually 7.
okay.
Yeah. Order. Yeah. You have to be able to output the solution.
Yeah.
Okay, so let's now talk about how we can parallelize the pivot algorithm. So instead of drawing these pivots on the fly, we can first fix a random permutation of the vertices. So say this is a random permutation, and then we process the vertices according to this permutation. So first vertex number 1 would be a pivot. We cluster it with its neighbors. Vertex 2 is now clustered, so the next vertex to consider is going to be 3. That will be the next pivot, and we continue so on and so forth until forming the clusters. Now we can parallelize this in the following way. We again draw a random permutation. Suppose we take the same permutation, and now instead of in the first round just marking 1 as the pivot, every vertex whose rank is smaller than all of its neighbors, we can safely assume that it's going to be a pivot. So the moment that we reach that vertex, it's going to be a pivot. So in the first round, other than 1, we'll be sure that, for example, vertex 6 is also a pivot because its neighbors are 7, 9, 14, and 13. So in the first round, we'll actually find 3 pivots. And what we can do is we can remove them and their neighbors, and now do the same on the remaining graph. So now the only vertex whose rank is smaller than its neighbors is going to be 3. So we can remove 3 and its neighbors and continue. So now the question is, okay, now we're putting vertices into, like we're picking pivots more aggressively. Does this help the round complexity of the algorithm?
You actually didn't get this clustering, right?
Well, yeah. So what we do is we first continue forming these pivots, and then when all the pivots are found, then that's when we form the cluster. Every vertex joins the cluster of the pivot among its neighbors that has the smallest rank.
Oh, I see.
Yeah.
Okay.
So it's important. That was a very good question. It's important to wait all the way to the end, and then see who's the pivot among your neighbors that has the smallest rank. Because a smallest rank neighbor could actually join later on. Yeah, so it's important to wait until the end and then form the clusters. Okay, so, but importantly, the outputs are the same. Now the question is just what's the number of rounds. And in a nice paper, Blowak, Feynman, and Sean in 2012 showed that for random permutation, this process actually turns into log squared n rounds. So it's much faster than forming the pivots one by one. And later on, Fisher and Nover tied them down, showed that the right answer is actually log n. They showed a deterministic log n rounds, and that there are instances on which the high probability takes log n rounds at least. So this parallelization of the pivot algorithm achieves a log n round algorithm. It's much better than n, but still we prefer constant rounds in any of the settings I mentioned. Okay, so how do we make this a constant round algorithm? So we'll modify the algorithm and we'll truncate it. So we'll follow the same parallel approach. So we continue forming the pivots, but we terminate the process after R rounds. So suppose that R is 1 now. So we will take the local minimums, that would be 1, 8, and 6. We know that their neighbors are not going to be pivots, but we have no idea if the white remaining vertices are going to be pivots or not. So we want to now form the clusters. So what do? Every pivot that we find starts a cluster, and a vertex joins the cluster of a neighboring pivot if it is sure that it's going to be my pivot. So here, for example, vertex 15 sees a pivot 8 among its neighbors, but it's not sure if it's the right pivot or not because 3 and 4 are also its neighbors and they could potentially be pivots. So what we do is for these vertices that do not know which cluster they should join, we just put them in single clusters. So this is the clustering that we would get for one pivot.
But 3 is also like a local minima in its neighborhood. Oh, sorry, it has 2. Because the edge.
Yeah, it has to. Yeah. Any questions? All right. Okay. So as we increase R, of course, this gets closer and closer to the output of the pivot algorithm. If R is log n, we'll get exactly the same output. But now the question is, if R is small, constant, say 1 over epsilon, do we get a good approximation? Okay, so let's see 2 examples. The first example is when the input is just a collection of disjoint cliques. In this instance, the optimal cost is 0. So if you want to claim any multiplicative approximation, you better find the optimal solution. And indeed, just after 1 round, the minimum vertex of each clique is going to be marked as a pivot, and we will form the optimal clusters. So this is good. Even for R1, we get the optimal solution. This is a bad example. So here we have a clique. Attached to it is a path, and this path is monotone. And the ranks along this path are all smaller than the ranks in the clique. So what happens is, this is the output of pivot. It has cost 3 only for these 3 red edges crossing the clusters. So now let's run our pivot for R equals say 3. So in the first round, the only vertex that's a local minimum is 1. All other vertices have at least 1 other neighbor with a smaller rank. So in the first round, we only find 1. In the second round, we only find 3. In the third round, we only find 5. And we terminate here, and no vertex in the clique sees a pivot. So we put all the vertices of the clique in singleton clusters, and that means we have to pay for all these edges going across.
Isn't this a very unlikely permutation?
Exactly. Yeah. So we want to argue that these types of permutations are unlikely to happen if the starting permutation is random. So the algorithm doesn't actually perform this early, when the permutation is random in expectation. Okay. So, but this immediately motivates that to analyze the approximation ratio. What we need to do is to bound these chains of dependencies. And this is exactly what the machinery developed for Sublinear algorithms does. There, we do it for time complexity. We want to explore a small neighborhood to see if a vertex is matched or not, if it's an independence or not. Here, you can use it to analyze the approximation ratio. Yeah, I don't have time to go through the details of how the analysis works. So yeah, I'm gonna skip this slide because I want to talk about another application as well. So I have like 2 minutes. Right? So this is the second application that I want to mention. A few years ago, in 2019, with Matla, Mamatari, Cliff, and Madhu, we proved that if you take a graph G, and also take the graph G from which you remove an arbitrary vertex V, and draw the same permutation, random permutation on both, and run the pivot algorithm, then the expected number of vertices whose cluster changes in the 2 outputs is at most log in expectation. And we proved this lemma because we wanted to design a fully dynamic algorithm. The graph changes over time, we want to maintain, say, the output of the pivot algorithm. In particular, based on this lemma, we were able to show that a 3 approximation of correlation clustering can be maintained in polylog n time after each edge insertion or deletion to the graph. And again, the proof of lemma 1 heavily relies on the machinery developed for sublinear time algorithms. And I also want to end with saying that beyond correlation clustering, this lemma 1 has also been used for K-center by a recent work of Botany, Esfandiari, Jairam, and New York in Soheil 22. They showed that there is a 2 plus epsilon approximation of, there's an algorithm maintaining 2 plus epsilon approximation of K-center by spending over K time per update. And this is, in a sense, optimal, but K is needed for an update. Yeah, so I believe that there's a lot more to explore. And if you have an application that you think sublinear time algorithms could be helpful in clustering, I'd love to talk about that. And if you're interested in sublinear algorithms, I just want to say that there's going to be a really nice science program this summer on sublinear algorithms. I'll be there. So yeah, if you want to chat, that would be a great place to attend. What?
How is the logo related?
Oh,
Thank you. Waiting you to signing up.
yeah. Yeah, so I just want to end with this meta open question that what are some more applications of these sublinear time algorithms, and in particular this local query process? Yeah, with that I'm going to finish the talk. Thank you very much.
Any questions? So actually, could you give us a sense of like how you use those technical results? The
Query
complexity, exactly, the ground complaint.
Oh,
So the results of the last 2 slides, like after our rounds, you know, you would be pretty close to the answer. Yeah.
so the analysis of approximation. So the number of rounds of the algorithm is by design R.
Right.
So you terminate after R rounds.
Okay, but the approximation.
Yeah, the approximation. Okay, so in this clique example, I want to argue that, okay, so I want to charge this mistake that I make for this edge in the clique. So how do I charge this? I run exactly the same query process on the vertices of this edge. So take an edge, I want to say if I make a mistake, okay, run that recursive query process defined in the sublinear time algorithm. So for this 14 and 7 edge, we would first query 6 to see if it's a pivot or not, then it would query 5, then it would query 4. I would get this long path. And then what happens is, if the algorithm after some R rounds puts these 2 vertices in singleton clusters, then the stack of recursive calls should at some point reach R. Okay. Take the first moment that it reaches R, the last 3 vertices of the path must form a bad triangle. What's a bad triangle? It's a set of 3 vertices, 2 of which are neighbors. Like, well, the ones along the path are going to be neighbors. But these 2 vertices must be non-neighbors, or otherwise 3 would first query 1 before querying 2. And what happens is, no matter how you cluster vertices of a bad triangle, you're going to have to pay the cost. So we can charge that bad triangle. Another question is how many times is a bad triangle charged? And that we use the found in the sublinear time query complexity analysis to show that it's not going to be a lot. Great.
Any additional questions? Okay, if not, then let's thank others.